already. Just for the avoidance of doubt, this is graphical models, so hopefully you're on the right place. So I guess I should just give you some general sort of advice about the program or the module. Maybe some administrative things to start with. There's a Moodle page. Hopefully you all know about Moodle. So the password is EM 12. Okay, so if you go to this Moodle page, you'll find all the notes, the lecture slides, etc. So this is the Moodle page. So there's not a huge amount there visible to you at the moment, except the general course outlines. There will be some. This is the place where we will post all the stuff. So all of the assignments, exercises, etc. will all be done through this Moodle page. Also the hand-ins, etc. will all be done here. So you need to get pretty familiar with this page. I probably will also turn on. There's a kind of like a forum page as well. So if you want to have a discussion about yourself, then you can do that there. I'll also email people. So if there's any kind of like changes to the course, or is there for some reason we kind of made the lecture one day, then it will be done through here. Okay, so we're not. You need to check it. Hopefully you get an automatic email sent to you. I don't know exactly how it works. Okay, so it's 11 weeks we have. We have 5 weeks to teach, and then we have a reading week, and then we have another 5 weeks after that. During the reading week, you will be kind of hopefully using that time to catch up or maybe do assignments, etc. On Fridays, there is also a sort of tutorial class, so that on Friday morning, I think, something like 9 o'clock, I don't remember exactly the time, but you see our timetable. And the purpose of the Friday mornings will be to kind of help you with some exercises. So the way it's going to work, typically, is that on Wednesdays, I'm going to ask you to look at a certain set of exercises, and I'll explain where these exercises are to be found shortly. And you basically, you will tend to do those for Friday, so you don't have a lot of time, unfortunately, so you've only got a day and a half, something like that. And then we'll go through the responses or the solutions on Friday, or whatever else you prefer to discuss. Okay. So the Friday will be quite a sort of flexible time, but this is the framework that we would like you to do. So it could well be that the first week you don't manage really to get through all of these exercises, so they'll carry over through to the next week. Right? So it's very important that you try to keep up with this. This is the way one mechanism we have for assessing how well you're coping with the course. Again, as usual, our experience is that if you're not coping well with the exercises, you will not cope well with the whole module. So, we will be 50% coursework, 50% exam. Okay. So that's quite a lot of coursework. So we'll discuss that in a minute. Before I forget, let's just go through where you get these things from. So if you click on this link here, this takes you to this page here. Okay, so there's a book that's associated with this lecture course, and you can either download it for free here online, or you can buy it. I forgot what the price. If you want to take a look at the copy in the break, then feel free to.
Do you give discounted versions of it? It's your book.
Sorry?
Do you give discounted versions?
Yes,
of the book?
well, I don't personally give a discount, but there is I believe at the moment, a promotional discount, which I don't know if it's still active. Oh, it's 36 quid. So it used to be 45, but it's 36. I mean, I personally get a discount, you know. If I get a discount of 40%, I think. So what's 60%, 45? It's less than that, right? Yes.
That's 20%.
Is it 20%? That's bad. I believe I might be able to get a higher discount than that. I'm not quite sure. I'll get back to you.
Do you give that to friends and family?
Last year we did something like that. You know, I ordered a huge number for students, and then they just gave me money. But just let me get back to you on Friday about what the actual details are of that. But certainly, I mean, it's up to you guys. I mean, take a look at the book anyway. It's not, you don't need to have a hard copy, but some people prefer to have these hard copies. All right. Of course, this will take a little bit of time to arrive. It'll take a few days to get from CUP or Amazon, and then they have a. You can also order it through Amazon as well. There are lower prices. Okay, so go back to. Here, so this web page contains a lot of other stuff as well. So you can also download some software here. So this is a MATLAB toolbox. So a lot of the demos and exercises, assignments will be using MATLAB. And to use the MATLAB well, there's also a toolbox of routines for this course. Okay, and you can download that toolbox here, and I would recommend to use this object-oriented version package. This is a kind of obsolete code, non-object-oriented stuff. I don't really maintain that anymore. Okay, so it should be reasonably clear how to use this stuff, and you just maybe just try a few demos there. You'll see me using this toolbox as we go along today, and you should find it quite straightforward. Okay, now there's other stuff down here. There's some errata, so there are some typos, some small errors in the book. I kind of put them up there. Instructor's material, you don't get access to this, that's great. That's just for course instructions. That's it, pretty much. I don't know how Octave is working with this new object-oriented stuff. So if you have not got MATLAB and you prefer to use Octave, you may be somewhat forced to use the old code, but I'm not sure if Octave is fully compliant with all the object-oriented aspects of that. Okay, any questions about this? So go there, download the book, the software. Okay, so okay, so this is the general frequently asked questions. Just some general info about the course. So, like I said, there are going to be some assignments that will be 50% of the course. The assignments actually will be group-based project work. So you'll be working in smaller groups. What that means is that within the group, you're totally free to discuss amongst yourselves. It will be a group effort. But it's okay. And I would ask the exercises and assignments here again through the page or in class as well. Typically, I would imagine there will be 3 to 4 assignments, and they'll be quite lengthy. So it will take you some considerable time to do these assignments. And some of them will be more straightforward, some of them will be less straightforward. And I will include something which is quite challenging. Some of the parts of the assignments will always be difficult. But the idea is to try to give you a graded sort of set of things which will both help you learn the material but also challenge you as well. So I think, advice on these kinds of things is that helps with maybe some of the other modules as well. You should spend, you should spend time on this stuff, but it's perhaps not great to spend weeks of work on something which is, you have to think a little bit about how to balance your time. If it's getting critical in terms of time for you, then maybe you should move on to another question of the assignment. It's just not maybe worth spending 3 days just to get another 1%. That's not good use of your time. Okay, so so the exercises, these are separate. They are not graded, the exercises, so they don't count your marks. But of course, implicitly, they help you get a good score in the exam. So you should see them. The lecture notes from the book, essentially they are covering the first 12 chapters of this book. That's a little out of date, so it already appeared in 2012. So this is very important. So what I do here, this sort of me standing up here, is just a kind of small part of our course, really. So the course consists of you reading the notes, doing the exercises, doing the assignments, and this is like a small fraction of the whole thing. This is really just a kind of a pointer. I'll give you some slides, but you really need to go all the way and understand the material. And also, very happy to have quite informal sort of discussions in Wednesday sessions. Partly because there's a huge amount of material you can read. Everything pretty much is there in some sense. So maybe we can use this time as a kind of aid to understand the written material. However, I should say beyond that, this is not a correspondence course. It's critical that you come to these lectures and also the Friday tutorials, because I will give out hints throughout the whole time about what is likely to be coming up in the exam. Okay, this is to encourage you to come to the lectures. So also there will be additional things we will discuss in here as well in the room, which will be examinable. Potentially everything that I discuss here is examinable, but it may not necessarily be in these lecture notes. So you need to come. All right. Any questions on that? No? Frequently asked questions. Well, I don't know. From previous years, can you provide the lecture slides before the lecture? Yes, hopefully they should all be there. They are there. Moodle page for this week. Can you provide written solutions to the exercises? So on the Friday, typically we'll go through the solutions on the whiteboard. We may provide you with some written solutions, but only right at the end of the program. Okay, not whilst we are going through the course. So that's simply because, again, we want to encourage you to come. Otherwise, there's a danger you will just see this as a correspondence course, you just accept the material, and you don't come to interact, which is really probably one of the most useful aspects. In the exams in the third term, there's no MATLAB tuition, I'm afraid. So if you're struggling with MATLAB, let me know. You can try to address that in some way, but hopefully most of you will not find that problem. Similarly, if you're really struggling with this course, then of course let me know. So you should also see the Friday class actually as a way to help resolve things that you don't really understand very well. So I will do this Friday, but in general there'll be a teaching assistant, someone else, not me, who will do the Friday morning class. His name is Chris. He'll give you the details about that. So another question is this a really hard course? I know some people think I'm a really stern guy, so they get worried and this is a really hard course. Maybe I am a stern guy on the surface, I don't know, but it's not a hard course, I would say that. But statistically, it's not a hard course. So most people pass. So my take a little bit is to be not tough, but I think I want to be realistic and make sure that you work reasonably hard, and so that you're in good shape to pass the exam. And very few people fail. I don't remember how many, but it's one of the most passed modules on the program. I think we already covered what is the difference between this and the Gatsby course, yeah.
We have to submit our choices of modules, some in Tumblr, some just for Tumblr. So if we decide to take this course for the exams, but we do so in, let's say, in January or December, is that possible? If we have submitted the coursework and so we can change final submission.
So which exam are you going to take? Which, say with this one or the Gatsby?
Yeah.
So I'm not.
Can we
you can
can
switch.
switch later?
Yes, I believe you can do that. Yeah. I don't know but I know that there is various sort of stages which you have to declare which modules you're going to take, etc. But I believe that the initial stage is not a formal declaration in stone, in concrete, what you're going to take on the exam. I believe you can modify that. But obviously, this is something that's important to try to understand as soon as you can do, because obviously, for example, if you're doing the Gatsby and this in parallel, that's a huge amount of work. That will be to the detriment potentially of your other modules. So you want to try to, if you can do, come to a kind of understanding with yourself as soon as you can. But it's difficult, but it's
One more question.
Yeah.
You say that this course focuses on discrete variables.
Yes.
And Gatsby mostly on continuous.
More.
Yeah. More. Is one of them more important for computer scientists or?
Well, I think historically computer science is more about discrete. So it's not that one is more important than the other. For machine learning, we do most things, many things are in continuous variables. I think what this course is about is trying to, the thing that's really important is not whether or not it's continuous or discrete, but the underlying concepts. And the concepts are actually the same depending on whether or not it's discrete or continuous variables. The only real difference there is just some technical things. So maybe you need to know some multivariate calculus to implement these concepts in a continuous case. So here we're kind of trying to get access to those concepts without some of the technical sort of things that you may need for continuous variables. That's it. This will probably go into some more depth than some topics in the Gatsby may do, and the Gatsby probably will cover more topics. So this will probably cover less topics, but perhaps a little bit more depth than the Gatsby. Okay. Okay, so I think that's it. Any questions?
I think we've been talking about it when you've explained the different modules. So how does the course relate to implementation methods?
Well, basic methods is not necessarily about graphical models, so that's just I haven't seen that course completely. But graphical models are about structure and distributions. So applied basic methods doesn't necessarily have to discuss graphical models. I'll talk a little bit about what graphical models are in a minute. Okay, so I think we have 3 hours, which is quite a long time. That's it. So it's up to you guys how we want to addition these 3 hours. My suggestion would be that I rattle on for about an hour and 20 minutes, then we have a say 20-minute break, and then we convene. Alternatively, we could say do 50 minutes, and a 10-minute break, and then another 50 minutes, 10-minute break. It's up to you guys. I don't mind too much. What would you prefer?
I prefer one break.
One break?
Yeah, one
Who
break.
goes for one break? Who goes for 2 breaks, 2 10-minute breaks? Okay, so I'm
The
gonna
one
use
break.
Alright. So the other thing to say is if I get excited and I've forgotten the break, just let me know. So if I get this right now, we should have a break at 12:20, right? So then we'll reconvene at 12:40. Okay, any more questions? Okay, great. So what the heck are graphical models? Basically, graphical models are ways to describe probability distributions. And probability is a very nice general framework. It's very good for obviously dealing with uncertainty. But it's actually quite a painful framework as well. So many of the old style things in AI and knowledge sort of representation trying to get around the fact that probability is really a kind of a monstrous thing to work with computationally. So what we tend to try to do is we try to reduce the computational burdens by using graphical models. And what they do is they structure the distribution in ways which make it simpler to work with. Okay, so we will use these graphs, the marriage between graph theory and probability theory, to kind of encode certain kinds of independence constraints and constructions which we may have a priori about a particular problem of interest. Now you may think this sounds all very theoretical and kind of a bit abstract somehow, but it's critical to know this. This actually is the dominant methodology or framework in all of machine learning. So you cannot do any, well, that's a little bit of a generalization, I'm trying to motivate you. Someone told me the other day about apparently all generalizations are wrong. So anyway, but it will kind of, I think it's true to say that if you do, for example, computer vision, if you do the inverse modeling, all of these things use graphical models. Okay, so anything to do with probability is using graphical models. All kinds of information theories use graphical models. Engineering uses graphical models. It's become the dominant framework. So what you will find is that you might go to some courses, after this one, and say, oh, now I see, that's a particular graphical model which is used there. So what we're going to focus on here is trying to give you the overarching theoretical constructs, and we will do some more practical things, but they will not be so specialized in a particular application. This is more the general picture. Okay, so that's it, basically. Okay, so we're going to start with the first lecture. This is going to be an introductory lecture, so I apologize for remember this is all very familiar, but hopefully we'll get a little bit more interesting to explore. Full screen. So like I said, please download these. Obviously today is a little bit unfortunate because you didn't have access to the page yet, but you'll get these each week. So what I would suggest, you should really try to read through these slides before you come to the lecture, ideally as well. So probability is the following kinds of things. So we're going to think about discrete variables at the moment. So I'm going to use this kind of notation. So x is going to be a variable. It could be, for example, a coin. And so this sort of sans serif thing is just going to represent the state of the variable. So for example, it might be heads or tails. And this thing, p of x equals x, I just mean that's the probability that the variable is in the state x. So what's the probability the coin is heads? So that might be, say, a half. Some number between 0 and 1. And this number just represents a kind of degree of uncertainty or certainty we have about what state the variable is in. The domain I'm going to call just represents a set of states that the variable x can take. So again, the domain of a point might be heads and tails. I'm going to use this notation a little bit. So when summing over a variable x, I write this kind of notation here with some function of x. I mean that I'm summing over all states of the variable x. So this is kind of shorthand for summing over states which are the domain of x, f of that functional value of each of the states. So if you've given a domain of a variable and you specify the probability of every single state, and these states are sum to 1, probability sum to 1, then we have a distribution of the variable x. So you need to specify these positive probabilities such that they sum to 1. Then we have the false case, then we have a distribution. Yeah.
In the case of the summation and the redundancy.
Yeah.
So in that case, we'll be summing both the heads and the tails in the case of the
Yes.
point.
This is really just more, hopefully, notation for most of you. You may have, studied this with slightly different notations. So the operation, so the and, so we're going to have now two variables, so x and y, and we're going to have a joint state for x and y. This is going to be a joint distribution. It's not a single variable or a joint. There's more than one variable. What x comma y means is the variables x and y. So you might, have other notations. It's more set theoretic notations in some places, or maybe the operator and, etc. But if, just to show you, I'm going to use this comma notation, and what this means really is this is just a way of indexing a kind of a joint state of this distribution. So it doesn't really matter if I write p of y comma x or p of x comma y. I'll show you a little bit later why that's true, but in probability notation, typically we're just using this to access, to index a particular element of an array. And how we do that indexing, it really doesn't matter how we relabel these variables. Okay. And this is a little bit different from sort of standard mathematics, where the function is not necessarily invariant to reordering of the variables. So in probability, it typically is. Marginalization, so if you're given a joint distribution x and p of x and y, this is the definition of a marginal. Okay? It says that p of x, the definition of that is the sum of the states of variable y, the joint variable, the joint distribution p x and y. Okay, so some people sometimes ask me, like 1 week before the exam, how do you show this? I know it's a definition, okay, of probability. That's the marginal. And more generally, if you say that a collection of say n variables, you could sum out, say, the ith one, we get a marginal on the remaining variables. We could repeat this and then sum out 2, 3. Because of the interchangeability of summation, it doesn't really matter if I write this, which order I do this summation. Okay, so you know what a probability distribution is, you know what a joint distribution is, you know what a marginal is, and I'm going to use, this is probably the most important definition in the whole course. I'm going to define conditional probability of x given y by this thing. So it's defined to be the ratio of the joint distribution divided by the marginal. Okay, this is just a definition. And it's a definition which makes some sense, as we'll see later. And this is really a critical thing for Bayesian inference and reasoning in general in probability. This simple looking rule will actually enable us to kind of do really magical things. It's an extension of classical logic, and it's really quite fundamental. So if we take this thing here, right, we can write from there px comma y equals p x given y p of y. Okay. And if I said that px of y is equal to p of y and x, I can also write this. So these two things are equal. So we can write on the left px given y x, so we divide by py. So we get this relationship. This relationship is typically known as Bayes' rule. So there are some different definitions of what Bayes' rule is. It doesn't really matter. Okay, some people, including myself, typically define this to be Bayes' rule. Other people define this to be Bayes' rule, but they are correspondences. They are the same thing. So it doesn't really matter. And indeed, if you go back to the original literature from Mr. Bayes himself in 17 whatever, it's completely unclear what he meant. At least I can't understand what he was trying to do. Now, this kind of thing enables us to do very simple reasoning. So let's imagine that you're throwing darts. So a dartboard has got 20 sectors. From 1 through to 20. And let's say that you're told that the dart has not landed in region 20. What's the probability that it's landed in region 5? Okay, so if it's not in 20, it's somewhere up at here. So there are 19 sort of slots left. What's the probability it's landing in 5? Well, if it's uniformly going to land anywhere else, then it's going to be 1 in 19. There's only 19 conditions left. That's the intuitive answer. I'm just going to show you that this is what you get by using the space rule. This condition. So by definition, it's the probability of region 5 and not region 20. So not region 20 is this whole sector here. If you intersect that with region 5, you've just got region 5. So this is this. And on the bottom you've got not region 20. So the probability of region 5 in priori is 1 in 20. Probably not region 20 is 19 in 20. So you get 1 in 19. So this is the logical, sort of intuitive result.
So can I ask, your example there, isn't that a bit one-dimensional then? When you're talking about x and y, surely it has to be two-dimensional. So sort of your dartboard but with an x and y axis.
No, these are just two variables or two statements. It's all in general. So here, this is x and this is y. They don't necessarily correspond to some fifth dimension or something like that. They're just kind of descriptions of variables which are describing your environment. And you could have many of them. They may not necessarily all be independent. They could be somewhat related in some way to each other. But they're just ways of you as the modeler, you can decide yourself which variables you want to use to describe your system. So here we have all kinds of variables. What's the sum of are we in the left or the right half? With all kinds of descriptive variables. This interpretation, this conditional probability, you should not really think about this as a causal thing. It's not necessarily implying that given something happened, what's the probability that something else is going to happen? It's really just, the best way to think about this is just about states. And this is going to tell you which states are accessible given the information. And then this would just be the probability given that information of which states are accessible. But that's not necessarily causal. But we'll come back to this a little bit later. Alright. So just to show you how this is all going to work in a computer, we're going to give a little example. So here's a simple one variable model which has got 3 states. And the variable is the country on the Great Britain. And the states are going to be whether or not you live in England, Scotland, or Wales. And this is the sort of if you like, the percentage of people in Great Britain that live in England, Scotland, and Wales. So a priori, if you said, a person just sort of randomly picked from Great Britain, what's the probability they live in England is 88%. I just make these numbers up, by the way. So it doesn't, what we're going to do is we're going to store this object, this vector, in the computer. And I think it's intuitive. It doesn't really matter. If I put the 0.88 at the down at the bottom, just, always use that as the third element of this vector. And I use, say the other two stay the same, I suppose. I need to change them. It doesn't matter how I do the indexing. As long as I'm consistent, whenever it says, in this case, I want to know what's the probability, that the person lives in Scotland, that they know it needs to go to the second index of this graph. That's all it means. I mean, it's up to you. You may prefer to put its third index. As long as you're consistent in accessing this, it's irrelevant. And that's the origin of this interchangeability of px, y equals py from x. We don't care. It's just an indexing issue to how you decide. So let's look at how we restore a joint distribution. Here there are two variables. So we've got now which country you live in, but also which language you speak. So what's your mother tongue? So I'm going to write down, for example, a conditional probability. So when I have your mother tongue, maybe you speak English, Scottish, or Welsh, and you maybe live in England, Scotland, or Wales. And I'm going to write down some fictitious additional probability. So what's the probability, given your country, of which language your mother tongue? So what this would mean is that if you're living in England, the probability that your mother tongue is English is 95%. Although I suspect that's a bit optimistic, I suppose. Then, suddenly this would be given that you're in England, the probability your mother tongue is Scottish, 4%, etc. Okay, so what you should find here is that these columns, they all sum to 1. Because no matter what this state is, this is the probability distribution itself. Okay, so this must sum to 1. So how do we see that from here? So how do I know that this is a probability distribution that sums to 1 and I sum all the states of x?
When you write it out and sum. From your definition of Bayes' rule,
Yeah.
I mean, you start writing out and doing the summation.
Well, we can just sum it, right? We could say, let's sum this over x. So, we sum this over x. This denominator is a constant. By definition, this is equal to the sum over x and the value of x. This was defined to be the marginal. So that's S equal to that. So we have to have, whichever way you decide to do your indexing, in this particular case I'm doing it column-wise, that my columns have to sum to 1. Otherwise this is not a correctly specified distribution. So if you like, in some sense all what we're doing is we're using this variable to slice through the dimensions of this array. And we can similarly we could have more dimensions here. We could have all kinds of numbers of variables, and we're just indexing, storing them in some large arrays, and we're just going to be using some kind of indexing in the computer to access particular elements of this space. What I could do then, I could, for example, define a joint distribution over the two variables, which country you're living in, and your mother tongue, by multiplying these two. So from this Bayes rule initial probability definition, this thing here is equal to the joint distribution divided by this. Well, what that also means is that this, of course, is equal to the product of these two. So I just defined this, and I defined that previously. So what that means is that this joint distribution now is given by this table, which I could write out this way here. So is it the case that the columns of this joint distribution sum to 1? No. Does anything sum to 1?
Yes. entire matrix.
The entire matrix. Because you have to sum over all the states. And all the states are x on two variables here. So what that means is that you have to access every element of this array, whatever dimensionality it has, and take that sum, and that must sum to 1. If it doesn't, there's a screw up somewhere, either in your definition or in your computer program. And the marginal from this joint is defined by either summing column-wise or row-wise. Okay, so if I get this right, the probability of the country is given by summing over the variable states of the variable molecule. So that's going to be summing over by the row. So you should find that we sum these variables here, these values here, because you get 0.08. Right? I might get this one row. Okay. So the rows, we get this. Otherwise, the other variable, you're going to get a probability of monotone is given by summing a country, which will correspond to summing the other way to get these two new distributions. And these, what can you say about them? Do they sum to 1? Yes. Good. Okay, so this is nice, it's all kind of consistent. These are distributions, joints are distributions, the marginals are distributions, the conditionals are distributions, everything's okay. Right? So it's all making sense. That's it. That's all there is to cover on discrete variables. There's nothing more. That's all the things. Okay. Now, so you might think this is fine. I can get a job at Google with this stuff. There's no problem. And the problem is, though, that if you're doing machine learning or you're working with Google or whatever it is, you're going to have lots of variables. Maybe all kinds of descriptions of your customers. There could be thousands of them. There could be millions of them. If you're working with images, there could be many, many more than that. So if you want to use the framework of probability theory, this means that you're going to have to specify distributions on potentially millions of variables, or very large numbers of variables. Now let's think about that in this discrete case. So to specify a distribution over one variable, which has got n states, I need to specify the values of each of those n elements of that vector. And similarly, if I've got, say, two variables, let's say they each take n states, but I've got this matrix, right, this square array, and there'll be n squared elements there to specify. They're actually n squared minus 1 and n minus 1 because there's a normalization constraint which is going to reduce the number by 1. But so you can see in general, to store n, so just to store how many variables, a k variables, for n variables which each take k states, we're going to have k to the power n entries to specify these tables. So this is exponentially big. So what this means in practice is you can forget about using probability theory without any other restrictions for more than about 10 variables. It's hopeless. It's impossible. It's not a question of I'll get a faster computer next year with a bigger hard drive. It's just not going to happen. It's just combinatorially bad. That's why graphical models are here. They are here to get around this issue, to help you resolve this. That's why they're fundamental. So physics, chemistry, all of the sciences are using graphical models. They may not call them that, but they've been using them for at least 100 years in physics. They've been around for at least 50 years in statistics. But maybe only recently we started to coalesce on sort of calling them all the same. There used to be different names for these things in communities, but now we decide to call them graphical models. And similarly with information theory, etc. These are, in some cases, they've revolutionized science. They've helped a lot to communicate ideas across different sub-branches of the science. And in some cases, they've enabled algorithms which were applicable in one area to be used in another area. So, for example, in information theory, it's been an absolute revolution the last 15 years. People are now able to do things which were thought inconceivable 15 years ago. All the new generation of error correction mechanisms will be based upon graphical models. Just to give you one example. And this is something which solved the problem, one of the biggest problems in science in the last 100 years. So these are major things. People have won Nobel Prizes for working with graphical models in physics. These are major, some of the biggest intellectual challenges in science are here. And we're all using this framework to understand how to communicate what these challenges are and the algorithms which are. Okay. So let's step back a little bit from the heavy heights of Nobel Prizes to Inspector Clouseau. Maybe this is not maybe a little bit more confusing example than it used to be, but I'll just try to give you a flavor for how to think about problems in model. So Inspector Clouseau, he arrives at the scene of the crime. His butler, maid, I think there are two main suspects. It could be somebody else, because he has two main suspects. Now, because he's such a great training, he has a prior belief of 0.6 that the butler is the murderer. The prior belief of 0.2 that the maid is the murderer. So it could be that somebody else is the murderer. Two probabilities. But these probabilities are independent in the sense that probability of the butler and maid factorizes. And I'll come back to this definition in a minute. Okay, so we're going to try to, so the idea is that we're going to try to use probability to model a scenario or an environment, a universe sometimes. So the thing we do is we first identify the variables which are going to be playing a role in this environment. So here we're going to have the butler, the maid, and we're going to have the knife. So I can say there. So the I should say that later the inspector will see that there's a knife which is being used in the crime, and this is also going to play a role. So it's going to be three roles: butler, murder or not, maid, murder or not, whether or not a knife is used in the crime. And so he's going to formulate Inspector Clouseau. This is just his a priori knowledge about butlers, maids, crimes, and knives involved in crimes, etc. And he says, well, okay, the domain of the butler and the maid are the same, either the murderer or not the murderer or whatever else. The domain of the knife is whether or not the knife is used or not. So he says, the probability that the butler is the murderer is 0.6, probably the maid is the murderer is 0.2. So again, in places of extensive criminal knowledge, he says, well, if the butler was not the murderer and the maid was not the murderer, the probability that the knife was used in the murder is 0.3. Okay. This is just his criminal knowledge, which he's gained and experienced over the years. Okay. And he sort of encodes that. Then he comes along to the actual crime scene and he finds out that the knife actually was used in the murder. And then the question is, what's the probability that the butler was the murderer? So what I'm trying to impress on you here is we've got a collection of variables, we've got some probabilistic definitions of these distributions, and now we want to do some inference. We want to understand what's the probability you infer something about whether or not the butler was the murderer given knowledge about the knife being used. So I want to figure out what's this conditional probability. Now, the problem is that we don't have direct access to this. We only have direct access to a model which contains three variables: butler, maid, and whether a knife is used. So what I'm going to do is I'm going to take this joint distribution. I must make reference to the joint distribution all the time. So just formally speaking, I can get access to that joint distribution by introducing this maid variable here, the states of the maid variable, something over them. So this, E, by construction or by definition, is just a margin of this conditional joint distribution over states of the variable maid. this, by definition, is just the joint distribution divided by UK. Okay. And now we can use the fact that the probability distribution specializes into P of so we have the P of the butler, the maid, and the knife. Which is P of knife, maid, times by probability of butler and maid. By definition. And I told you in the problem set up that this actually is going to factorize. So that's what you see here. Now I've got the joint distribution, which splits in this way, where I know these will be specified now by factors O. So we can then plug this into here. We're going to have to sum this whole thing over the numerator of the states of the maid. So we can do that there. And the denominator is simply P of K, but that's given by P, K, B, and M summed over B and M. Okay, so that's given by this thing here. And I can pull out, simplify some of these factors which are not dependent on B. Okay, so this is the mathematical computation I need to carry out. And then I can use the actual fact that the knife was used, and I want to know whether the state of B the murderer is. Okay, so I can then, what's the probability B? Well, P of B is the murderer, what was the murderer, which was 4.6. Okay. And then what I'm doing here, so I have to sum over the states that the maid was the murderer, so the maid was the murderer was 0.2, I think. And then the probability that the knife was used, given that the butler was the murderer and the maid was the murderer, was 0.1. Yeah.
Small m, is it the maid or is it the murder?
The states of the maid. Okay, so we have the two states of the maid, just some over there, the corresponding probabilities, and then we have to carry out this boring calculation to the denominator, summing over the states of butler and maid. Okay. We'll carry out this whole thing and we get about 0.7.
What if we don't know exactly the probability of, for example, the maid having murdered the victim? Like, if we know that it's 0.2 plus or minus confidence interval, something.
Yeah, we'll discuss a little bit about that later on. That's called, one way to do that is with what's called soft evidence. But we'll discuss a little bit about that.
Is when you say the probability of the butler and the maid having murdered the that
Yeah.
they are independent,
Yes.
does this have a physical interpretation, like they murdered the victim independently, not having plotted?
But a priori, we believe there's no, if you like, collusion or something like that between these two.
So that would be the physical interpretation.
Yeah, it's just our a priori knowledge says that we have no reason to suspect that they, in some sense, are collaborating to do this.
And last one.
Yeah.
Are these examples practical in the sense of, for example, like
Real
what's it
police
called, like forensic evidence?
Yes. So that was a facetious answer, but they are used. Yes.
Because I've read something like, for example, somebody who smuggled, I don't know, something in the US, and then they, at the court, he was fined for everything he supposedly had smuggled the previous 5 years from statistical evidence. Like,
Right. So this kind of reasoning is used in court. The problem is that there was, I believe, a case some years ago where so they tried to use this Bayesian, it's not Bayesian, but this is kind of conditional probability reasoning. The problem was that because the UK court system is a jury-based system, It's not just a judge on their own. It has to be the mechanism. It was deemed in the end that the jury must understand the mechanism by which the verdict was reached. Right? Well, so because they were not unfortunately able to follow the logical reasoning of the probability, it was in the end dismissed as a valid technique in some sense. But certainly parts of this reasoning is used in courts. And obviously there are many other areas of use. So in medicine, for example, that's another very big area where this is used. But this is just really the definition of probability. You will see that when you do machine learning, it's like that. You say, given I have this data set as a training data set, that's conditioned. What's the probability that this new label will be classed as a positive example, something like that? And it will be exactly the same. We just need to specify a different model, much more complicated. So you might think, so some people are getting really confused about this denominator term here. So in this case, we're going to be calculating the probability that the knife is used. But I told you that in the setup, because no one knows that the knife is used. So you might say, well, that's 1. Probably the knife is used as 1. But that's not the case. So this is something you have to be. Your probability is really all about just making sure you understand what the conditions are. So here, this is the probability of knife is the prior probability of the knife. So it's not given anything else. There's nothing on the right of the conditioning bar here. There's no other knowledge. So if you say, well, what's the probability that this knife is used given that the knife is used? Well, that's this definition of distribution divided by that. There's no numerator, is just intersection of these two, just in itself. Then you get cancellation, you get 1. But that obviously, that holds, right? So you have to be very careful just to make sure you understand what information is there in the setup in the question. Okay, so let's move on to independence. So this is a definition. Okay, this has nothing to do with the rules of probability. This is just a definition, like conditional probability is a definition. So two variables x and y are independent. If knowing one event gives no extra information about the other event or variable. So what this means mathematically is that p, x, and y, the joint distribution, is a product of the two margins p(x) plus p. And we can use this joint definition in the conditional probability definition. And so we find out this is equivalent to saying p of x given y is equal to p of x, which is kind of intuitive, right? That's nice because it's given y, if x and y are independent, well, given y is just the same as given p of x. It doesn't tell you anything else. It doesn't give you any additional information that p of x didn't already tell you about this. And vice versa, there's a symmetry. P of y given x is equal to p of y. So that's the definition of independence. And this has to hold true for all states of x and y. It's not enough just that for some subset of the states x and y. This is mathematical or this numerical factorization of independence. It has to hold for all the states of x and y. It's again something you need to be careful about. And the notation that I'm going to use is, if two variables x and y are independent, I'll use this sort of strange bar notation here. This is actually introduced by Philip David, who used to be here at UCL. Statistical. So just to say, so x independent of y doesn't mean that given y, we have no idea what x is. That's not what it means. It just means that the only thing that you know about x is what's contained in p of x. So you may know a lot about x. You may know that x is for sure in state 1. So x, you could have a situation where maybe you have two variables. Y is not telling you anything, but you know absolutely what variable x is in. So x and y are independent. So you have to be a little bit careful to think about what this means. It's not that you don't know anything about x, it's just that y is not bringing you any additional information on x that you don't already know on the field x. And you may know a lot about x. You may know very little. So more generally, if two variables are proportional to product of two positive functions, x and y, they are also independent. How can you figure out, by the way, what is this k here?
Normalization.
The normalizing of f of x and
Why would you need the outside condition to absorb it to one of the f or the g's?
you could do that, but sometimes it would be inconvenient to do that. So you could do that. But let's imagine that somebody says, I want to have an explicit formula for k. How would you get that?
1 over the integral of w integral of b. Okay, integral of f.
Integral?
And integral of
Or in discrete, discrete variables.
discrete. That's not.
The sum. Okay. So that's true. So because the sum over x and y, p of x and y, equals 1, by construction, this means that this is equal to the sum over x and y, k of x. K is a constant. So it says that k is equal to 1 over the sum of x and y, x gy. And 1 over the sum of x of f of x, the sum of y gy. But this step here that I did is very important to understand. I just used this fact that I have a function here, a function over y, and I have to sum over the two variables. So, for example, if I'm summing over the variable y, whatever the state variable x is, it's effectively constant as I'm summing over the variable y. So what that means is that I can push this summation through here. Right? So it's like I'm carrying out this summation here. So it's kind of be some number, and then similarly I've got a sum left over x, and again that would now be just some number, so that's not varying with x. So effectively it just means that I can carry out these two sums independently. So what we are doing effectively here is we are distributing this summation operator over this product, and this will be a critical thing that we will do in the future. We'll distribute other operations over structured functions. And this works because summation is associative. So that's why you can do this. We can always distribute operators over structured functions like this, but in this case you can. And we will exploit this more system throughout the. If we didn't have this mathematical property, there would be no graphical models. So you need to make sure that you're comfortable with these algebraic manipulations. Or if you don't get this, you need to make sure you take that. So that's nice now. So we can recover what this constant k is now, just as this explicit function of these two functions here, f and g. So that's kind of nice. So what I'll often say in the future is, well, I may define some probability distribution up to some constant, and I say, well, of course you can always figure out what that constant is by normalization. In this case, I use the fact that this function factorized to make this thing even more simple, but in general it would just be 1 over the sum of the states of this whatever, if we just have of x, p of x is proportion to f of x, the constant proportionality is 1 over the sum of the states of f of x. So conditional independence. So this is going to be, I'm going to define this now just a little bit more generally. It's going to hold for sets of variables as well, not just single variables. So I'm going to assume that these sets of variables are mutually exclusive. They are not, they're not overlapping sets of variables. They're just different three sets, x, y, and z. So x is conditionally independent of y given z. What does that mean? Well, I'm going to define it to be that the joint distribution x and y given z factorizes. So x given z. And similarly, as a phase rule, it also holds that p of x given y and z is equal to p of x given z. So this is just exactly the same as before, except now we're just putting this additionally on the right of the conditioning bar. The whole thing follows x. And I'm just extending it to the case where I have sets of variables. Okay, so sometimes we will we'll just write this, x is independent of y, or I might write x independent of y given the empty set, just to mean the same as this, just x independent. So x independent of y, conditional of y given the empty set is just meaning that x is independent of y, unconditionally. Now, maybe a little bit of a, so probability is easy, we defined it in 5 minutes. The problem is the logical consequences of probability are quite hard to get your head around. Intuitive as a human, or maybe some of you are better at this than me, but there are many pitfalls waiting for you, bear traps, just for the reader. And everybody gets this wrong, pretty much. Not necessarily this particular example, but Nobel Prize winners, field medal winners. It doesn't matter how smart you are. It doesn't matter how you will get this stuff wrong. Usually, at some point, everybody gets some probabilistic reasoning stuff. Very counterintuitive. So, to give you an example, this is maybe not so difficult to see, but you might think that, let's say we have 3 variables, just x, y, and z, and I say that given z, x and y are independent. So in other words, for every state of the variable z, x and y are independent. So you might, and then I ask you, well, are x and y independent? You say, well, they're independent for every state, z, so surely they're independent. They're not. It does not follow that conditional independence implies marginal. So that's a fallacy, logical fallacy. But it's a very easy one to make, very natural. And there are many such logical fallacies that you can easily get wrong. So let's figure it out. So I said I want to know something about the marginal x and y. I want to know whether or not x is independent of y. What does that mean? It would mean that this joint distribution would factorize as p of x times by p of y. So I want to see if that's true. So I'll figure out what is p of x comma y. Well, by definition, this is equal to the joint distribution, the sum over z, p of x comma y from z. Equal to z x comma y given z times by pz. This is Bayes' rule. I'm making no assumptions here, except that just using Bayes' rule. Now, from conditional independence assumption of x and y given z, which says that they're independent, is equal to x given z, p of y given z. This is not generally true, but in this particular problem, I'm told that's the case. So that's what this expression is here. Now, if these were independent, what would it look like? It would be P of x, which you get from this, which is the marginal of Px z over z, for example, and P times by Py, which is the marginal of Py z over z. Now, these two terms here, they look tantalizingly similar with an x given z here, y given z, x given z, y given z, y given z, but the two pz's over here, they're not the same. Right? They're not the same. So it's not true. So the great thing about probability is that if you're in doubt, all you need to do is whip out Bayes' rule, initial definition of probability, and see if you can figure it out. You know, you kind of gets around these logical difficulties. So conditional dependence is the converse of independence. So if they are not dependent, they are dependent. Okay, so let's do an example before the break. So this is going to be another little modeling scenario. We're going to have three variables. The wife's car type. There are going to be four car types. There's going to be the husband's car type, going to be four car types, states. And there's going to be family income. So there are four car types. The first two are cheap. Car type 1 and car 2 are very cheap. The last two car types are expensive types. And we do the same for the wife and husband car types, and we use W for the wife's car type and H of husband's, and your income can be low or high, say family income. So you might say, what this one here is saying is, what's the probability that the wife will buy a cheap car, given that there's a low income family, is 70%. Probability she'll buy a cheap car type 2 is 50%. She's is a poor family, so they don't buy expensive cars. The wife won't have an expensive car. On the other hand, if it's from a high income family, the wife, she might still buy a cheap car. I mean, women don't need to have expensive cars. So they might still buy a cheap car. Why waste your money? On the other hand, for the husband, if if the family income is low, he might have a particular preference. Most guys would choose this car. This is kind of cool. It's cheap. It's cool. On the other hand, if the family income is high, there's no way a husband would buy a cheap car. He's sure going to buy one of the expensive cars. Let's say you know that the probability that family income is low is not the case. 80% of families income. And the question might be, given this setup now, we could define a joint distribution, and we might want to figure out various things. Like, for example, let's figure out whether or not the wife's car is independent of the husband's car. So, given the family income, I'm going to assume that these car preferences are independent of the husband and wife, given the family income. So if you know it's a high family income, you know that the husband's car preference and the wife's car preferences are independent. Similarly, if you know it's a high family income, high or low family income, they are independent. The question is, if you don't know whether it's a high or low income family, are the husband and the wife's preferences for cars marginal dependence question. So we can do that the following way. Both is the wife and the husband marginal distribution. It's given by exactly the same analogous expressions as here. Product, because I'm assuming they're independent, which is sum of the states of income, wife of income, times by total income. I've got four states of wife and husband. So I'm going to end up now with a 4x4 joint probability table. And I work all those things out, I get this. And if you put them correctly, you'll find that these numbers are something like that. From this, I can actually figure out the margin distributions P of W and P of H by summing the columns and summing the rows. This will give me P of W and give me P of H. There will be two vectors. Then I can figure out what is the joint product P of W, P of H, given those two marginal vectors, just by multiplying the corresponding elements together. And I get this value here. So you can see, numerically, they are not the same. Even though, traditionally, they were independent, marginally they are not. So yeah, I mean, you can maybe make some interpretation about this. So for example, in this case, you see that we don't have family income. If we know that the husband has a cheap car, then his wife must also have a cheap car. Therefore, these variables are dependent. So there may be some intuitive explanation you can make about this, but you can numerically check it. Okay, so we will, after the break, we'll discuss more about the numerical aspects of this. So let's reconvene at 22.
Yeah.